Okay. Thank you, Francisco Javier. Yes, my name is Lars-Göran Magnusson. I'm from Arctos Labs, and as we heard, we have for some time now been working on this idea to add automatic and also optimized placement to OSM, and that is what we're going to talk and also demonstrate in this session. So we will try to cover these things. Maybe I should set up a pointer in case we need. So what we'll cover now is our view of what we mean by placement, an introduction to the placement optimization we have now started to work with in OSM, thinking about different types of optimization, which also covers then possible future extensions to what we have now. We'll look a bit about different use case examples where this can apply. We'll have a look at how you invoke this feature, and then we end with the demonstration, so we show a bit of what you can do and what's happening and so forth. So this feature is now targeted for, let's say, the next OSM release. I think it says 7.1 somewhere and 8 somewhere, but next OSM release. So what you see now is a preview, we can say. So if we look into what we then mean by this placement optimization, in the lower left-hand side, we have a view of a network as it might look at for an operator. This is actually a picture that we have from the new white paper from the end user advisory group, which is released just now. So it shows that there is a lot of data centers, there's a lot of connectivity, so there is a lot of options as where you can position or where you can place your different VNFs and workloads and so forth. So in the context of OMM, from our perspective, placement is then about the process of deciding which VNF goes into which VIM. And we try to make this optimal, and in this case it's subject to the cost of the computes in the different VIMs. Typically things maybe are cheaper if you go to a global data center and more expensive if you have a local data center or even further down. Maybe we should mention that for those of you who hasn't read the white paper, CP in this case refers to customer premises, but we can also think about it as a network edge. In addition to the cost of using compute then in different VIMs, there is also a cost of using the links for the service interworking. And what we also apply then is constraints that could that we may want to have, or that is built in the network service. Now we talk about latency and jitter. There could be other things as well. So the idea with the placement future is to make this process automatic and optimal. We'll look into more details then. So we see this maybe as a piece of the puzzle to further enhance the automation that we're actually already working with within OSM. So in a way, it's a contribution to reach this zero-touch automation that we sometimes talk about. If we look about the actual process of doing these things, if we first start by thinking about, say, any software that we have, for instance, in some earlier talks we had today, we saw examples of requirements that we had on OSM itself. it requires some sort of resources, and if you don't have enough CPU or if you don't have enough storage, then it won't work. And the same thing sort of applies also to network services. So there are some sort of requirements that we can put on the network in order for the network service to actually work as expected. So this is sort of the constraint side. What we use now is we talk about constraints on the links. We can think about other types of constraints as well. And then these things then needs to match whatever kind of infrastructure that we have, that we see down here. And these have now, say, between the different VIMs, we have different characteristics for the links. There is also different costs. We have different costs of compute for the different VIMs, as we also talked about earlier. So what the placement function will do then is given these constraints on the network service, take and consider all the VIMs that is available to the user, check that these constraints are met, if there are any, not necessarily so. This is actually maybe a good thing. I mean, knowing that, okay, with the infrastructure that I have at hand, I simply can't fulfill the requirements that this service have. So that's probably also a good thing to know. If we look at future maybe capabilities, you could imagine, for instance, dry runs. So you could sort of test out, what if I do like this? Will my infrastructure support this service, or will I have to do something else? So we feed all these things, the costs, the link characteristics, the constraints, into this placement engine. And now we have this criteria to cost optimize. And then we will select the option that fulfills the constraints at the lowest possible cost. That is, where can we place the different VNFs in our infrastructure? So this sort of summarize what we try to do here. It's a computation of the optimal placement of the VNFs over the available VIMs for the user. And we do this by matching the specific requirements we have for this service to the infrastructure that we have available, paired with the metrics that we have, and then whilst considering the cost of the compute and the network. So you also here see that this is sort of the abstractions that we are currently working with in our current model. We talk about the NS, the VNF, the links, the VLDs, we have VIMs and VIM connectivity. So that's sort of the initial choice for abstraction level. There could be other options, and things can evolve in the future. Inside the placement functionality, all these things are modeled then as a constraints optimization problem. So the constraints, link characteristics, the cost model, and all these things are expressed in a model that is targeted for constraints optimization. So it first then checks that we can satisfy all these constraints, and then it computes the optimal solution to, well, you can view it as a bit of an equation system. That also means that it's also possible to fairly easily extend this model with new kind of abstractions and new things that we can take into consideration when we do this matching, and when we consider the metrics and the costs of different things and so forth. So if we look at this then component and how it fits into OSM, it's a new component, obviously. It's optional, so you will have to install it typically with a --PLA option. Not all these things are maybe ready yet, but that is how we think it will be. And as I mentioned, what we have now is sort of a basic functionality where we can express constraints on links in terms of latency and jitter. There could be other things that comes in the future. And it's also an optional thing that you need to invoke by giving a specific command. So if you don't specifically invoke it, it won't do anything. So NBI and LCM or LCM will see, oh, someone wants to have support for automatic placement, and go and ask the PLA component, how should we distribute these VNFs over the available VIMs and so forth. So this is done by now we show the CLI version here in the --config argument. We have new capabilities where we say placement engine is PLA, and then we say that the placement constraints is, and then whatever kind of constraints we have, we will look into more later on for these things. You could notice though that these things are sort of open-ended, so you could think about sort of different directives that comes here, and here we can think of all different kinds of possible constraints. As it is now, the constraints are given at instantiation time. It could also be so that some network services will sort of inherently carry their own requirements. So that's also a possibility that the information model actually contains a way to express these constraints for the developer of the network service. But as it is for now, we feed these constraints at instantiation time. And then, of course, the PLA has this information that we talked about, the cost, the link properties, and so forth. And now we should have a look at the different ways to do optimized placement, and these are then examples. So there are a lot of other things that is possible, but we start with the first one is, okay, we go for cost optimization only. So there are no constraints. We have a cost model. We request placement of a network service, and we compute the optimal placement based on minimizing the cost. That's sort of fair enough. And then we have another option that we sort of is working now today. You have cost optimization with latency constraints. So we have our same cost model here, but when we try to instantiate something, we add additional requirements on the link that the latency must meet these requirements, and the same for jitter as an example, and then we compute the cost using that criteria. And now we think about what could happen then in the future. Well, for instance, maybe you don't want to optimize on cost. Maybe you want to optimize on utilization, still with some sort of constraints model, and that would be also possible. You need to evolve the model a bit, and you maybe need to give another directive, and then we can sort of work with those kind of abstractions as well. And if we look further ahead in the future, I think, or maybe not further ahead, maybe closer ahead, capability constraints could be one thing that's really a good thing. For instance, we have exemplified here with maybe you have a VNF that requires GPU, for instance. Maybe you have an AI model that benefits from specific hardware. So then we could have that kind of thing that, oh, for this thing we need this kind of capabilities. There could be a lot of other things also. Naturally, you come to think about, for instance, affinity and anti-affinity, where things must be co-located or are not allowed to be co-located. That could be one thing. Regulations, you could think about, am I allowed to put the information that is processed within this VNF in this data center or in that data center? Could be one thing. You could also imagine, if we remember that the network model that we have with the different global and regional data center, we could have some sort of label matching and filter that says that this is a VNF that should go into the global data center, or this is a VNF that must be in the edge. So that's also some sort of capability views on this. And while we're at it, we could also maybe talk a bit about this cost model, because it's worth to think about it. It could be, and oftentimes is or will be, an absolute cost. I mean, this is what I have to pay to place this VNF in this data center, or this is what I have to pay to use this link. But it could also be so that you want to use it as a relative cost between different data center links, and if you want to bias the placement, if things are satisfied and there are still options, maybe we want to put sort of a fake cost, if you like, to a specific data center to increase utilization or something like that. So in that way, it works like a bit of a, maybe we could say, a sort of policy. So that's also worth thinking about, that cost doesn't necessarily have to be the absolute cost of things. Some examples of use cases here. For instance, if we have a UPF that we want to have to support low latency, where do we put it? Well, then we typically want to have placement as close to the customers to achieve the latency constraint. That is, also deploy as close as it has to be. Another option we have over here is where we look for the transport optimization for different application components. So in this case, we have an IoT data processing. So then we might want to place close to the source of the data to reduce transport cost, or to reduce transport load, could be one thing. And in the bottom, we have an example where we think about, in this case, placement of LTE core network VNFs at the most effective compute. And this is actually quite interesting, because oftentimes we mentally think about this as deploy as close as it has to be. But you could also think about it, deploy as far away as it can be, because that might be cheaper. For instance, in the first talk today from Antonio about the Unica, we saw examples of maybe using public clouds, where things maybe is cheaper and have other characteristics that you want to achieve or use for some reason. And then it's really interesting to know how far away can I put things and still have it working, still fulfilling these requirements that we put on the service. Okay, how do we invoke this thing? We've seen part of this before. So first version, we just request cost optimized placement, no constraints. We give this in the nscreate command. We could also add cost optimization with pinning of specified VNF, and I think this is essentially almost always happening, because there is always, I suppose, or always, at least in most cases, there will be some sort of anchor point where some VNF has to go somewhere because it needs to be close to some user, it needs to be close to some other application or some other function in the network. And then here we now start to see examples on how we request placement with cost optimization, but with constraints on the VLD in this case. So we have the placement engine PLA, and now we start talking about placement constraints. What we have now is constraints on the VLDs. So we identify the VLD, and this is sort of using the terminology and entries that you have in the NSD. So we will actually look then in the NSD to identify what things we are talking about here. So we identify this VLD, and then we put link constraints on it. We say the latency has to be better than 120 and the jitter has to be better than 20. And then you can sort of match these things. For this other link in this example, well, there are no latency constraints for some reason, but we want to have a jitter constraint because it will not work unless we have that kind of characteristics fulfilled. And then, of course, you can do a combination of these things. So we pin some of these things. We say that, okay, this VNF has to go there. And for the links, which could relate to this one or be totally unrelated to this VNF, the following constraints apply. So now we show this for the command line, but of course this works also from the GUI with or without the YAML file, following the normal procedures. So a bit more about this pinning thing. Here we see 3 different examples where we just say auto. Here we say auto for VNF1 and for VNF2. That implies that, okay, there is no VIM specified. So here we have to compute the best possible VIM to place this VNF. And number 3 should go to VIM number 3, and a different number of different combinations here. So what one would maybe want to have here is the possibility to pin a VNF to, for example, the VIM that has a specific VNF. For example, this needs to be where the packet gateway is. This needs to go to a VIM that has connectivity to a specific PNF, could be one thing, or this has to go to a VIM that is related to a specific customer location. So typically these things will then, I assume, then come from OSS or even up in VSS, where you can maybe in some cases know these things, where things has to go depending on where users are or other things that influence these decisions. So again, what we do here is finding out where the VNFs should or must be deployed in a setup where we have multiple VIMs. So a bit about demonstration now. We'll show 3 different scenarios. In one scenario, the first one, we don't pin anything, we don't put any constraints, we just say that put this as optimal as possible, cheapest possible way. In the next scenario, we pin one VNF to a specific VIM here. And in the third scenario, we pin a VNF to another location, following the model we saw earlier. And then we also put an additional requirement that the link between VNF2 and VNF3 must fulfill these latency requirements. So this is the model that we have now. We have this global data center, a local data center, and two different customer premises, following the model in the white paper. Then they have different kind of link characteristics with costs and different kind of latency in this case, and the VIMs have also cost for deploying a specific VNF to them. So we have, in order to make it a bit easier to follow and see where things end up, we have this map where we show these things. So we can switch here, and then we can start by instantiating scenario A. As you see, no special requirement. We invoke placement by giving this command then. So now LCM will see that, okay, placement is requested. It'll do some requests to PLA and start then working with R and distribute these things. So then in this case, everything's all the VNFs end up in the global data center. Reasonable, because things are cheaper there, and we put no requirements on other things. Let's see where we have. There we have scenario B. What we do now is we say that, oh, but this VNF, it has to go to this specific VIM. So in that case, the situation should be a bit differently. Now we force it to be placed in one VNF in a specific location. And then we can calculate, but where do we put all the other ones then in relation to this in the cheapest possible way? So what happens here in scenario B then is that we pin this one here, and then given the costs for placing the other ones, we find out that, okay, one goes to the global data center and one goes for this local data center. And then if we further complicate things a bit, here we have then scenario C. Now we pin one of the VNFs. We use a different VIM in this case, but we also put additional constraints, and we say that the link between VNF2 and VNF3 has to satisfy these latency requirements, which is a bit of a different situation. So if we launch that, we'll see then we should see one VNF ending up here, and then we can think about where the other one goes. And okay, so what happens now is that since we added a bit tougher requirements, actually, we can no longer put the third VNF in the global data center. It has to go here to satisfy the latency requirements. So it will turn out to be a bit more expensive compared to scenario B. On the other hand, we then fulfill the requirements that we had on this service. So that sort of illustrates things, and you can sort of think about what happens if we change this to 18. Does that change anything? And sort of, if you're like me, you start thinking, okay, let's see, then we have one there, and then we have the latency cost, and then the possible links and so forth. Some of you maybe see this obviously, but it just goes to show that even in these kind of limited and pet examples that are really simple, it's still not really that obviously where the optimal position in this case for cost actually is. Okay, we see in the demo. So as we said, this is sort of a first release. OSM itself is now in release 7 and is sort of production ready, as we've seen earlier today. this thing is a bit more basic, and we would appreciate any community feedback so we can evolve this feature. We had a session yesterday on the ordinary text sessions where we showed a different demonstration where we talk about interaction with BSS and how you could sort of place a UPF in relation to a user in an optimal way, which gained some attention. So we are thinking about arranging a follow-up session on placement, maybe next week. It's not decided yet, but if you're interested to know more or has any ideas, you can contact either Mats or you can contact me. I'm also available on Slack, on the OSM Slack, under this name. So I suppose that's about it. Maybe I've extended my time a bit. I'm sorry about that.
All right. No, but I mean, it's not too much extension. I mean, I've seen that there were a couple of questions in the chat. So probably would be good that I mean, maybe if the people who posted in the chat want to speak up and answer questions now. I see that Ana Hermosilla, Logan Schumacher, and Jean-Pierre Conti posted a few questions. So
Yeah, I haven't had time to check the chat, but I can do that.
No,
unless we should take them, unless we take them now.
Yeah. Yeah. So okay. Do you want to ask your questions now, or Anna?
Okay. I was thinking if there's any estimated time on which the new improvements to the placement platform is going to be offered.
No, our target now for the basic releases is sort of next OSM, and then we want to collect more of this community feedback in order to think about different kind of enhancement, whether this is capability matching or utilization or something else. So, but as I said, the model is quite extensible. So for some new requirements, it's maybe not a lot of work. For some, it might need a bit more analysis. But the basic functionality, I think, will go into the next release.
Okay.
And that's the roadmap we have now.
Okay, Logan, you have one question as well? And we will close with the third one with Jean-Pierre. Okay, so Logan. Are you still there with us? Maybe you are mute. That's why we can hear you. Okay, the question was, what are the dynamics of the placement in face of evolving constraints? For instance, how frequently does it make sense to reassess the optimality of the placement?
Currently, what we do is that we invoke this upon instantiation time. The placement engine is there at all times, and it's not really aware of when it is used. So, for instance, if OSM would invoke that in some scenario for redeployment, that would also be possible from the PLA component. Then you have to think about the possibility to actually migrate things and so forth. But I think there is an obvious service assurance aspect of this that could be further investigated.
And last question, Jean-Pierre, are you there?
Yes, very nice presentation. It's a simple question. Are you considering to include any artificial intelligence insights to support the placement?
Oh, this is better than artificial intelligence. No, seriously, I think, as I mentioned, what we have here now is a model that sees this problem as a constraints optimization problem, and for some definition or for some subdomain of AI, this is probably qualifies as some AI. What it is not is that it's not a machine learning thing if we think about what's popular today, because we believe that this problem doesn't lend itself very well to those kind of technologies. It is, from our perspective, an optimization or constraint satisfaction optimization problem. So you can't sort of have a supervised learner to have a lot of different data sets that we can learn these things, and it's also not the reinforcement problem, but still maybe it sort of qualifies as AI, in at least for some definition of it. I'm not sure if that really answers your question then, but that's sort of how we view it. We find the technology that is suitable to the problem at hand, I would say.
Okay, thank you.
Okay, so I think that we can close